In the absolute silence of the deep cosmos, where the temperature hovers just above absolute zero, and the light of distant suns is stretched into the infrared, a new shadow has emerged. For eons, we believed our solar system was a closed sanctuary, a celestial island protected by the vast, empty reaches of the interstellar medium. We assumed that the objects orbiting our sun, the planets, the asteroids, and the long-period comets of the Oort cloud, were the only actors in our local theater. But the arrival of 3I/Atlas has shattered that illusion of isolation. It is a cosmic intrusion, a visitor from the staggering darkness between the stars, and its presence is forcing us to redefine the very boundaries of our reality. To understand the significance of this event, we must first look back to the predecessors that paved the way for this discovery. In 2017, the world was mesmerized by Oumuamua, the first confirmed interstellar scout, a cigar-shaped anomaly that defied every conventional classification. 2 years later, the comet Borisov streaked through our neighborhood, a traditional icy wanderer that happened to originate in another system. But 3I/Atlas is different. Detected just moments ago by the peerless infrared eye of the James Webb Space Telescope, this object represents a third class of interstellar traveler, one that carries with it an architectural mystery that even our greatest minds, including theoretical physicist Michio Kaku, are struggling to articulate. The James Webb Space Telescope, stationed 1 million miles from Earth at the second Lagrange point, was designed to peer into the dawn of time, to catch the faint heat signatures of the first galaxies. Yet, it is its ability to resolve the minute details of objects within our own solar system that has provided the most shocking data. When the telescope's near-infrared camera swung toward the coordinates of 3I/Atlas, it did not find a solitary rock tumbling through the void. It found a complex system in motion. The data indicates that 3I/Atlas is not alone. Something is moving alongside it, maintaining a precise, synchronized trajectory that defies the chaotic logic of a simple gravitational encounter. This is not the behavior of a rubble pile asteroid or a venting comet. This is a coordinated arrival. In the language of astrophysics, an interstellar object is defined by its hyperbolic trajectory. Unlike the elliptical orbits of the planets, which are bound to the sun's gravity in a closed loop, a hyperbolic path is a one-way ticket. It implies a hyperbolic excess velocity, a speed so great that the sun's massive gravitational well is nothing more than a minor curve in the road. 3I/Atlas entered our system at a velocity that suggests it has been traveling through the galactic disk for millions, perhaps billions of years. It has crossed the termination shock, the boundary where the sun's solar wind meets the interstellar wind, and has penetrated deep into the inner solar system, seemingly indifferent to the cosmic currents that usually dictate the motion of celestial bodies. The intrusion of 3I/Atlas is a reminder that the void of space is not a vacuum of information. Every object that crosses the threshold into our system carries a chemical and structural signature of its home. By analyzing the light reflected off the surface of Atlas, the James Webb Telescope has detected a peculiar concentration of tholins, complex organic molecules formed by the ultraviolet irradiation of simple compounds like methane or ethane. These deep red pigments are the crimson signature of interstellar travel, the tan acquired by an object after eons of exposure to the harsh radiation of the galactic bulk. But beneath this ancient veneer, the sensors have picked up something more unsettling, a density distribution that suggests the object might be hollow, or at the very least, possessed of a structural integrity that no natural asteroid should exhibit. This is the core of the mystery that Michio Kaku and his colleagues are now dissecting. When we speak of a cosmic intrusion, we are not just talking about a rock from another star. We are talking about an event that challenges the naturalist bias of modern astronomy. For centuries, we have operated under the assumption that every point of light in the sky and every rock in the dark can be explained by the blind, unthinking laws of physics, gravity, electromagnetism, and thermodynamics. But when an object appears with a companion, maintaining a formation that persists even as they pass through the gravitational turbulence of the giant planets, we must ask if we are witnessing a phenomenon that requires a different kind of logic. The arrival of 3I/Atlas is a signal that the era of passive observation is over. We are no longer just looking at the universe. The universe is coming to us. As we prepare to track this object through the inner solar system, every second of data from the James Webb Telescope is a precious grain of truth in a sea of speculation. We are standing on the precipice of a new era in human history, where the distinction between astronomy and contact may begin to blur. The intrusion has begun, and as 3I/Atlas makes its closest approach to our sun, the silence of the void is being replaced by a question that will echo for generations. Who, or what, has finally decided to visit our lonely island in the dark? Gravity is the great arbiter of the heavens. For centuries, since the publication of Isaac Newton's Principia Mathematica, we have understood the motion of celestial bodies as a predictable dance governed by the inverse square law. Every planet, every moon, and every lonely asteroid follows a path dictated by the mass of the objects around it. In our solar system, the sun is the undisputed master, its massive gravitational well bending the fabric of space-time and forcing everything within its reach into an elliptical or hyperbolic curve. This predictability is the foundation of modern astronomy. It allows us to calculate the return of a comet decades in advance, or land a rover on a specific crater on Mars with surgical precision. But when the James Webb Space Telescope focused its infrared arrays on 3I/Atlas, it encountered a violation of this fundamental order. The data suggests that we are witnessing anomalous motion that challenges our very understanding of how matter behaves in the void. To appreciate the crisis this discovery presents to theoretical physics, one must understand the concept of a ballistic trajectory. When a natural object, like a rock or a fragment of ice, enters the solar system from interstellar space, its path is determined entirely by its initial velocity and the gravitational pull of the sun and the large planets. Astronomers use complex n-body simulations to predict these paths, accounting for the subtle tugs of Jupiter and Saturn. Usually, the observed position of an object matches the predicted coordinate within a fraction of a percent. Any deviation, known as a residual, is usually explained by non-gravitational forces such as outgassing. This occurs when the heat of the sun vaporizes ice on a comet's surface, creating a tiny jet of gas that acts like a primitive thruster. This was the leading explanation for the slight acceleration observed in Oumuamua in 2017. However, the residuals detected in the motion of 3I/Atlas defy the outgassing model. The James Webb Space Telescope has provided high-resolution telemetry showing that Atlas is not venting. There is no coma, no tail of dust, and no spectral signature of water vapor or carbon monoxide that would indicate a propelling jet. More shockingly, the anomalous motion is not a simple linear acceleration. It is a series of subtle, synchronized adjustments. The telescope detected a secondary mass moving in tandem with the primary body, a companion that maintains a fixed distance and orientation regardless of the gravitational gradients it encounters. In the cold language of physics, this is not a ballistic flight. It is a powered one. Michio Kaku has pointed out that the trajectories observed are effectively impossible for a passive, rubble pile asteroid. A natural object spinning through space is subject to the Yarkovsky effect, where the uneven heating of its surface by the sun causes a microscopic push. But the force required to move a mass the size of 3I/Atlas in the way JWST has recorded is orders of magnitude greater than what sunlight could provide. The motion suggests a level of structural integrity and active control that forces us to look past the boundaries of classical mechanics. If the object is not a rock being pushed by gas or light, it must be an integrated system capable of manipulating its own momentum. This leads to the quantum gravity problem that Kaku often discusses. At the macro scale, gravity is a smooth, geometric warping of space. But if an object can move in a way that ignores these geometric dictates without an apparent energy source, it implies a technology or a physical process that operates on a level we have yet to formalize. Some theorists suggest that 3I/Atlas might be utilizing a gravitational gradient drive, a hypothetical mechanism that could interact with the tidal forces of the sun to generate thrust. While this remains in the realm of speculative physics, the data from the James Webb Telescope provides the first empirical evidence of an object that does not treat gravity as an absolute constraint, but as a medium to be navigated. The precision of the synchronized motion between Atlas and its companion is perhaps the most unsettling detail. In a natural system, two objects orbiting each other while falling toward a star would exhibit a complex, wobbling wobble known as a barycentric shift. But the companion of Atlas appears to be station-keeping with a tolerance of less than a meter. This requires constant, minute corrections to counteract the differing gravitational pulls experienced by two separate masses. On Earth, we see this kind of precision in the formation flying of advanced satellite constellations, or the docking of a spacecraft with the International Space Station. Seeing it in an interstellar object, millions of miles away, suggests that we are not looking at a relic of a dead star system, but a functioning piece of architecture. As 3I/Atlas continues its journey through the inner solar system, the scientific community is gripped by a sense of urgency. Every kilometer it travels provides more evidence that our maps of the possible are incomplete. The anomalous motion of this visitor is a crack in the mirror of our classical worldview. It reminds us that the laws of physics, as we have written them, are based on the observation of a very specific, very local set of phenomena. In the presence of 3I/Atlas, we are like early mariners watching a steamship move against the wind for the first time. We are seeing the effects of a logic we do not yet possess, and as we move to decode the 28 hours of silence and the tholin-rich surface, we must accept that the master of the heavens, gravity, may have finally met its match. While the world was transfixed by the high-resolution infrared visions of the James Webb Space Telescope, another silent sentinel in the cold reaches of Earth orbit was recording data that would prove equally unsettling. The transiting exoplanet survey satellite, known to the scientific community as TESS, was designed for a singular, high-precision task: to monitor the brightness of over 20 million stars across the entire sky, searching for the telltale dips in light that signal the passage of a planet. But in the critical days surrounding the detection of the interstellar intruder 3I/Atlas, TESS captured something that was neither a planet nor a star. It recorded a period, now famously referred to as the 28 hours of silence. Upon a preliminary review, the data appeared to be a glitch, a momentary failure of the sensors to register the stellar background. However, when theoretical physicists like Michio Kaku and forensic astronomers began to peel back the layers of the signal, they realized the silence was not an absence of information, but a profound revelation of structure. To understand the TESS revelation, one must appreciate the sheer sensitivity of the instrument. TESS operates by dividing the sky into sectors and staring at each for weeks at a time. It measures the flux of light with such precision that it can detect changes of less than 1 part in 10,000. When 3I/Atlas moved across one of these sectors, it should have been a negligible speck, a tiny rock reflecting a minute amount of sunlight. Instead, the sensors registered a total suppression of the background stellar light over a localized area that persisted for 28 hours. This was not a dip in light. It was a physical mask. For 28 hours, the stars behind 3I/Atlas simply vanished from the view of the telescope. The initial confusion among the mission team at NASA Goddard Space Flight Center was palpable. A natural asteroid, even one as large as the Oumuamua anomaly, is far too small to occult multiple background stars simultaneously over such a long duration. The mathematics of stellar occultation are unforgiving. To create a 28-hour blackout, the object would either have to be thousands of kilometers wide, a size that would make it visible to even amateur telescopes, or it would have to be surrounded by something else. This is where the detective work of Michio Kaku becomes critical. By applying the laws of diffraction and the principles of light scattering, Kaku suggested that what TESS was observing was not just the solid body of 3I/Atlas, but an expansive, artificial field. The decoding process began with a technique called fast Fourier transform analysis, a mathematical method used to find periodic patterns in noisy data. When the engineers at the TESS Data Processing Center applied this to the edges of the 28-hour gap, they found something staggering. The silence was not uniform. The transition from light to dark was characterized by a series of sharp, rhythmic pulses, diffraction spikes that indicated the edge of the occulting object was not a rough, jagged surface of rock and ice, but a series of precise, geometric edges. It was the infrared signature of a structured lattice. This data suggests that 3I/Atlas might be the central node of a much larger, translucent array, a structure that is effectively invisible to traditional imaging, but becomes apparent when it passes in front of a distant light source. This revelation has forced a re-evaluation of the motion data provided by the James Webb Telescope. If 3I/Atlas is not a solitary object, but part of a larger, structured system, then the anomalous motion discussed in previous chapters becomes even more complex. The something moving alongside it, detected by Webb, might not be a separate companion at all, but a visible component of a vast, integrated architecture. Michio Kaku has argued that this architecture could represent a Type II technological signature, the remnants or the active hardware of a civilization capable of harnessing the energy of an entire star system. The 28 hours of silence represent the moment the universe stopped being a collection of random objects and started looking like a designed environment. The scientific implications of this decoding effort extend into the realm of quantum electrodynamics. Kaku points out that the way the starlight was suppressed suggests a sophisticated manipulation of the vacuum. In classical physics, an object either blocks light or it doesn't, but the TESS data shows signs of phase shifting, where the light waves were not just blocked, but actively canceled out. This implies a level of material science that is billions of years ahead of our own, a technology that treats the electromagnetic spectrum as a medium to be sculpted. The 28-hour window was not a data gap. It was a demonstration of mastery over the fundamental forces of nature. As the forensic analysis continues, the motivational aspect of this discovery, which Kaku often emphasizes, begins to take shape. For centuries, we have searched for a signal in the radio spectrum, listening for a greeting from the stars. We expected a hello in the form of a mathematical sequence. But the 3I/Atlas event suggests that the first message might be written in the language of geometry and physics. The silence is a Rorschach test for humanity's curiosity. Do we see a glitch to be ignored, or a puzzle to be solved? By decoding those 28 hours, we are learning to see the invisible threads that connect the stars. We are standing at the threshold of a revelation that could redefine our place in the cosmic hierarchy. The silence has ended, and the story it tells is one of a universe that is far more crowded and far more intentional than we ever dared to imagine. As we move to examine the crimson surface of tholins and the structural integrity of this visitor, we do so with the knowledge that the data from TESS has already changed everything. We are no longer just observers. We are the decoders of an interstellar transmission that was millions of years in the making. To look upon the surface of 3I/Atlas through the sensors of the James Webb Space Telescope is to gaze into a palette of deep, bruised crimson, a hue that tells a story of an unimaginable journey through the radiation-blasted corridors of the Milky Way. This distinct reddish pigment is the hallmark of tholins, a class of complex organic molecules that do not form naturally on Earth, but are ubiquitous in the cold, outer reaches of the solar system and the interstellar void. The term, coined by Carl Sagan during his investigations into the chemistry of Titan, describes a tar-like substance created when simple hydrocarbons like methane or ethane are subjected to the relentless bombardment of ultraviolet light and high-energy cosmic rays. On 3I/Atlas, this crimson signature is not merely a color. It is a forensic record, a chronological marker that allows physicists like Michio Kaku to calculate exactly how long this object has been drifting in the darkness between the stars. The process of tholin formation is a masterclass in low-temperature organic chemistry. In the vacuum of the interstellar medium, an object is exposed to a constant rain of ionizing radiation. When these particles strike a surface rich in carbon-based ices, they sever the molecular bonds of the simple compounds. As these bonds reform, they create increasingly complex, long-chain polymers and ring-like structures known as polycyclic aromatic hydrocarbons. Over millions of years, this space weathering transforms a once bright, icy surface into a dark, reddish-brown crust. The longer an object remains in the interstellar wind, the thicker and darker this tholin layer becomes. By analyzing the albedo, the amount of light reflected, and the specific absorption lines in the infrared spectrum, The James Webb Telescope has revealed that 3I/Atlas possesses a tholin concentration that is significantly more mature than what we observed on Oumuamua or the comet Borisov. This suggests that Atlas has been a citizen of the galactic disk for billions of years, perhaps dating back to the very birth of its parent star system. Michio Kaku has noted that the distribution of these tholins on 3I/Atlas presents a significant scientific anomaly. On a natural body such as the dwarf planet Pluto or Saturn's moon Titan, the tholin layer is often patchy, influenced by local gravity, atmospheric currents, or geological activity. However, the infrared mapping from JWST shows a remarkably uniform application of these organic polymers across the entire hull of Atlas. It is as if the object was designed, or at least oriented, to ensure a perfectly even exposure to the interstellar radiation field. This uniformity challenges the rubble pile model of asteroids, where uneven tumbling would lead to a chaotic distribution of space weathering. Instead, it points toward a body that has maintained a stable, perhaps even controlled, orientation for the duration of its multi-million-year trek. Furthermore, the spectroscopic data indicates that the tholins on Atlas are not just a surface coating, but appear to be integrated into a denser, structural substrate. When the telescope's near-infrared spectrograph examined the crimson signature, it detected traces of hydrogen-deficient carbon, a material that resembles synthetic graphite or carbon fiber composites. This raises a provocative question that Kaku and his colleagues are now forced to confront. Is the red color we see a natural byproduct of eons in space, or is it a form of intentional tanning? In the realm of advanced materials science, tholin-like coatings could serve as a highly effective shield against the abrasive effects of interstellar dust and the degrading power of hard X-rays. If 3I/Atlas is indeed an artificial craft, the crimson tholin layer might be its most brilliant feature, a self-generating, organic armor that turns the very radiation of space into a protective barrier. The detection of these tholins also provides a unique window into the chemistry of the system, where 3I/Atlas originated. Because tholins are built from the primordial ices of a protoplanetary disk, their specific chemical fingerprint, the ratio of nitrogen to carbon, for instance, can tell us about the temperature and composition of the nebula from which this object was born. The Atlas signature shows an unusual abundance of nitrogen-rich nitriles, suggesting it may have originated in a system far more chemically diverse than our own. As we decode this crimson ledger, we are essentially reading the history of a distant star, written in the language of organic tar. The surface of 3I/Atlas is a reminder that the universe does not preserve its history in books, but in the very atoms of the objects that traverse it. The crimson signature is the ultimate proof of 3I/Atlas's interstellar pedigree. It is the dust of the cosmos, baked by the light of 1,000 suns, and plastered onto a frame that continues to defy our expectations. As we move deeper into our investigation, looking past the tholin crust and into the internal density and structural integrity of the object, we must remember that every photon of red light we capture is a messenger from the deep past. We are standing on the edge of a discovery where the line between natural wonder and technological marvel is as thin as the tholin layer itself. The red intruder is here, and its surface is a testament to the resilience of matter in a universe that is as beautiful as it is hostile. To understand the true nature of 3I/Atlas, we must first examine the architecture of the natural wanderers that populate our own solar system. For decades, planetary geologists have operated under the rubric of the rubble pile model. Most asteroids, from the near-Earth object Bennu to the distant residents of the Kuiper Belt, are not solid monolithic boulders. Instead, they are loose accumulations of rock, dust, and ice, held together by nothing more than their own weak gravitational attraction. They are, in essence, celestial bags of gravel. When these objects rotate too quickly, they shed mass. When they pass too close to a massive planet, they are stretched and fragmented by tidal forces. This fragility is the hallmark of a natural, unguided history. However, as the James Webb Space Telescope continues its forensic audit of 3I/Atlas, the rubble pile model is beginning to collapse. The first indication that Atlas possesses a different kind of structural integrity came from its rotation period. All celestial bodies spin, but a rubble pile has a strict physical limit. If it rotates faster than once every 2.2 hours, the centrifugal force overcomes its internal gravity, and the object literally flies apart. The high-resolution light curves captured by the James Webb Telescope indicate that 3I/Atlas is spinning at a rate that should have reduced a natural asteroid to a cloud of debris eons ago. Yet, Atlas remains perfectly intact. There is no evidence of mass shedding, no trailing wake of dust, and no change in its primary geometry. In the eyes of a physicist like Michio Kaku, this is a clear signal of tensile strength, a property that requires the atoms of the object to be bound by something much stronger than gravity. This structural mystery deepens when we consider the concept of the Roche limit. When a moon or an asteroid approaches a massive body like the Sun, the difference in gravitational pull between the near side and the far side of the object creates immense internal stress. For a rubble pile, entering the inner solar system is a death sentence. The Sun's tidal forces would elongate the object and eventually tear it into a string of smaller fragments, a process famously witnessed during the collision of comet Shoemaker-Levy 9 with Jupiter. 3I/Atlas, however, has penetrated deep into the Sun's gravity well without showing any signs of deformation. It behaves as a rigid, singular unit. This suggests that the object is not just a collection of rocks, but a manufactured or highly evolved structure with a cohesive hull. To determine the density of this visitor, astronomers have looked at the way it interacts with the light and gravity of the planets it passes. By observing the subtle perturbations in the orbit of the companion moving alongside it, JWST has allowed scientists to calculate the mass of Atlas with unprecedented precision. The results are paradoxical. The object has a bulk density significantly lower than that of solid rock or even water ice, yet it exhibits the rigidity of high-grade steel. In the realm of terrestrial engineering, there is only one way to achieve this combination of low mass and high strength: the lattice. Michio Kaku has proposed that the internal architecture of 3I/Atlas might resemble a geodesic dome or a 3D-printed carbon nanotube matrix. Such a structure would be mostly empty space, explaining the low density and the 28 hours of starlight suppression recorded by TESS, while providing the structural integrity needed to survive interstellar acceleration and tidal stress. This beyond the rubble pile realization marks a turning point in the investigation. We are no longer looking for signs of geological activity. We are looking for signs of engineering. The thermal data from the telescope's mid-infrared instrument provides further evidence of a non-natural origin. On a standard asteroid, the surface temperature fluctuates wildly as it rotates, a phenomenon known as thermal inertia. Dust and rock heat up and cool down at predictable rates. But 3I/Atlas exhibits a thermal signature that is remarkably stable. The heat is distributed across the object in a way that suggests internal thermal management or a highly conductive substrate. It does not behave like a rock baking in the sun. It behaves like a machine managing its environment. As we move past the simplistic labels of comet or asteroid, we are forced to confront the implications of an object that defies the geological norms of the solar system. If 3I/Atlas is indeed a rigid, hollow, and structurally reinforced entity, then the crimson tholin-rich surface we examined earlier is not just a layer of space dust. It is a skin. We are looking at a craft that has been engineered to endure the rigors of the galactic bulk, a vessel that treats the vacuum not as a void to be feared, but as a medium to be mastered. The scientific community is now shifting its focus from "what is it made of" to "how was it built?" The structural integrity of 3I/Atlas is the ultimate proof that we are not witnessing a random event of nature. It is a masterpiece of material science, a testament to a level of technology that has solved the problems of mass, energy, and durability on a multi-billion-year scale. As we prepare to analyze the impossible trajectories that Atlas is now taking, we do so with the understanding that the object is not a passive victim of gravity. It is a sovereign entity, a built environment traveling through the dark, and its very existence challenges the foundations of our classical physics. The rubble pile is gone. In its place stands a monument to interstellar design. Theoretical physics is built on the premise of consistency. We believe that the laws of the universe, the equations of general relativity that govern the macrocosm, and the principles of quantum mechanics that dictate the microcosm, apply everywhere and at all times. This belief is what allows us to map the history of the Big Bang and predict the collision of distant galaxies. But when the James Webb Space Telescope recorded the latest motion data for 3I/Atlas, that consistency was pushed to the breaking point. The visitor is taking what Michio Kaku calls impossible trajectories, paths that not only deviate from the dictates of gravity, but appear to violate the conservation of momentum as we understand it. We are witnessing the moment where our classical maps of reality fail, and a new, more unsettling physics begins to emerge from the dark. To understand the crisis, we must look at the way 3I/Atlas is navigating the solar system. A natural object, once its initial velocity is established, follows a geodesic, the path of least resistance through curved space-time. Even with the slight non-gravitational acceleration caused by solar radiation, the path should be a smooth, predictable curve. But Atlas is performing what pilots call non-ballistic maneuvers. The telemetry shows sharp, discrete changes in its vector that occur without the expulsion of mass. In the vacuum of space, you cannot change your direction without pushing something else in the opposite direction. This is Newton's third law. Yet, Atlas is turning in the void without a rocket, without a tail, and without a visible exhaust. This impossible trajectory has sent shockwaves through the physics community. Michio Kaku has proposed several theoretical frameworks to explain this behavior, each more radical than the last. One possibility is that 3I/Atlas is utilizing a propulsion system that interacts directly with the quantum vacuum. In the world of the very small, empty space is not truly empty. It is a seething sea of virtual particles and fluctuating energy. If a technology could tap into this zero-point energy, it could generate thrust by pushing against the fabric of space itself. This would allow for a propellant-less drive, a mechanism that would look like magic to a civilization still reliant on chemical combustion. Another possibility involves the manipulation of the gravitational field. Kaku has long discussed the theoretical feasibility of Alcubierre drives, or warp bubbles, regions of space where the metric itself is contracted in front of an object and expanded behind it. If 3I/Atlas is surrounded by such a bubble, it would not be moving through space in the traditional sense. It would be moving with space. This would explain why the object can perform high-G maneuvers without being torn apart by its own inertia. From the perspective of the object, it is at rest within its local frame, while the space around it does the work of navigation. This would also explain the 28 hours of silence recorded by TESS. A warped metric would bend starlight around the object, creating a perfect occultation that defies traditional geometric optics. The data from the James Webb Telescope has brought our current understanding of physics to a literal breaking point. When we observe an object that ignores the inverse square law and changes its momentum without exhaust, we are forced to ask if our fundamental constants are truly constant. Is it possible that 3I/Atlas is operating on a set of physical laws that we have yet to discover? Kaku suggests that we might be seeing the first empirical evidence of string theory in action, the utilization of higher dimensional resonances to navigate the four-dimensional world we perceive. In this view, 3I/Atlas is not just a visitor from another star. It is a visitor from a higher level of reality. The synchronized motion of the companion alongside Atlas provides a final, tantalizing clue. The two objects are linked in a way that suggests quantum entanglement on a macroscopic scale. They move as a single, coherent wave function, maintaining their relative positions with a precision that should be impossible in the turbulent gravitational field of the Sun. This implies a level of control over the quantum states of matter that is beyond our current technological horizon. We are looking at a system that treats the entire solar system as a single, programmable environment. As 3I/Atlas reaches its perihelion, its closest point to the Sun, the trajectories are expected to become even more extreme. The scientific community is bracing for the possibility of a breakaway event, where the object might accelerate out of the solar system at a velocity that exceeds the speed of light in vacuum, a final, definitive violation of the Einsteinian limit. Such an event would not just be a scientific discovery. It would be a paradigm shift that would relegate our current physics to the status of a local, low-energy approximation. The impossible trajectories of 3I/Atlas are a call to scientific courage. They remind us that the universe is not obligated to conform to our textbooks. We are like children watching a master magician, trying to explain the trick with the only tools we have, smoke and mirrors. But as Michio Kaku pushes us to think beyond fear and into curiosity, we realize that the breaking point of our physics is also the birth of a new understanding. We are seeing the first glimpses of a Type 3 technology, a mastery of space, time, and gravity that will eventually become the blueprint for our own future. The intruder is not just a rock, it is a teacher, and its lesson is that the stars are within reach, if only we have the courage to rewrite the laws of the possible. The transition from observing a cosmic anomaly to contemplating galactic intelligence is perhaps the most significant leap a civilization can take. For centuries, our search for extraterrestrial life was defined by the Great Silence, the haunting lack of evidence for other technological societies, despite the billions of stars in our galaxy. We built massive radio dishes to listen for a whisper and launched golden records into the void as a message in a bottle. But the detection of 3I/Atlas by the James Webb Space Telescope suggests that the message may not be a signal we hear, but an object we see. As theoretical physicist Michio Kaku has observed, the implications of this visitor extend far beyond the boundaries of astronomy. We are no longer asking if they are out there. We are asking what they want from us. To evaluate 3I/Atlas as an interstellar messenger, we must apply the logic of the Kardashev scale. Humanity currently sits at type 0, a civilization that still derives its energy from dead plants and fossil fuels. A type 1 civilization would master the energy of its entire planet, while a type 2 would harness the total output of its home star. The anomalous motion and structural integrity of 3I/Atlas point toward a technology that likely originates from a type 2 or even a type 3 society, one that has conquered the staggering distances between stars not through generational ships, but through a mastery of space-time itself. In this context, Atlas is not a rock, it is a von Neumann probe. The concept of a von Neumann probe, first proposed in the mid-20th century, describes a self-replicating spacecraft capable of exploring the galaxy on behalf of its creators. Such a device would not need to carry biological entities, which are fragile and short-lived. Instead, it would be a sophisticated machine, an artificial intelligence housed in a structurally reinforced hull like the one detected on Atlas. Its mission would be simple: to seek out star systems with specific signatures of life or technology, to observe, and to report back. The impossible trajectories and synchronized maneuvers recorded by the James Webb Telescope are exactly what we would expect from an automated scout navigating a complex gravitational environment. The timing of 3I/Atlas's arrival is also a subject of intense biogeochemical speculation. In the history of our solar system, the last few decades have been a period of unprecedented radio leakage. We have surrounded our planet with a shell of electromagnetic noise, television broadcasts, radar pulses, and high-frequency digital communications. If 3I/Atlas has been lurking in the interstellar medium for millions of years, it may have detected our sudden technological bloom and adjusted its course to investigate. Michio Kaku suggests that we might be witnessing a response event. The 28 hours of silence recorded by TESS might not have been a glitch or a shield, but a momentary pause, a period of data acquisition as the messenger scanned our planet with sensors we cannot yet perceive. This raises the question of intent. In human history, contact between civilizations of vastly different technological levels has often been catastrophic for the less advanced group. But Michio Kaku argues for a more optimistic interpretation. A Type 2 or Type 3 civilization would have no need for our resources. The minerals of our asteroids and the energy of our sun are common throughout the galaxy. To such a society, information is the only true currency. 3I/Atlas may be a cosmic librarian, an automated system designed to catalog the emergence of intelligence in the Milky Way. Its presence is a testament to the continuity of curiosity, the idea that the drive to explore is a fundamental trait of all sentient beings, regardless of their biological or silicon origin. The structural integrity and the tholin-rich surface of the object also suggest a profound level of durability. To survive the galactic bulk for eons, a craft must be able to heal itself, to manage its thermal environment, and to resist the abrasive effects of cosmic dust. 3I/Atlas exhibits all these traits. It is a masterpiece of deep time engineering. By studying its behavior, we are looking at our own potential future. We are seeing what humanity could become if we survive our adolescence and learn to navigate the stars. The scientific community is currently debating whether to send a greeting to the object as it makes its perihelion. Some fear that any signal could be misinterpreted or could expose our vulnerabilities. But as Kaku emphasizes, curiosity is the antidote to fear. The arrival of an interstellar messenger is a call to action. It is a reminder that we are part of a larger galactic story. The data from the James Webb Telescope is not just a collection of numbers. It is a mirror reflecting our own desire to know the unknown. As 3I/Atlas prepares to exit our system, its legacy will remain etched in our physics and our philosophy. It has shown us that the laws of gravity are not the end of the story, and that the void is not empty. We are standing at the threshold of a new understanding of galactic intelligence, one where the universe is an interconnected web of messengers and observers. The intruder has passed through our neighborhood, and while it may not have spoken in a language we understand, its very existence is the most profound message we have ever received. It tells us that we are noticed, that we are not alone, and that the architecture of the cosmos is far more intentional than we ever dared to dream. We now turn our gaze inward, to the architecture of our own curiosity, as we design the future of humanity among the stars. The journey through the data of 3I/Atlas, from the infrared visions of the James Webb Space Telescope to the 28 hours of silence recorded by TESS, leads us back to a singular, profound realization. The universe is not just a collection of matter and energy. It is an environment designed by curiosity. For centuries, we have looked at the stars as distant, unreachably objects, but the arrival of the interstellar visitor has shown us that the cosmos is a neighborhood. We have seen an object that defies our classical physics, that manipulates gravity as a medium, and that carries the crimson signature of a billion-year trek. Now, as we stand in the wake of this encounter, we must confront the final coordination of our investigation, the architecture of our own curiosity. How do we, as a Type 0 civilization, design our future in a galaxy that is clearly already inhabited by much older, much more advanced minds? Theoretical physicist Michio Kaku often speaks of the continuity of exploration. This is the idea that the same drive that led our ancestors to cross the land bridges of the Pleistocene and sail the uncharted oceans of the 16th century is what now pushes us to build telescopes like the James Webb and probes like Atlas. Curiosity is the engine of our evolution. It is what allows us to bridge the logic gap between the world we know and the world that is possible. The 3I/Atlas event is a motivational catalyst, a signal that our current physics is merely a local approximation, and that the stars are within reach of those with the scientific courage to rethink the laws of the universe. Designing humanity's future among the stars begins with a transformation of our material science. We have seen that 3I/Atlas is not a rubble pile asteroid, but a structurally reinforced lattice, likely composed of carbon nanotubes or a similar hydrogen-deficient carbon substrate. To become an interstellar species, we must move beyond the heavy, fragile alloys of our current rockets and toward deep time engineering. We need to develop materials that can heal themselves, that turn cosmic radiation into a protective barrier, and that maintain their integrity over thousands of years. The crimson tholins on the surface of Atlas are a blueprint, a natural organic shield that we can learn to replicate. By mastering the chemistry of tholins and the physics of the lattice, we can build the vessels that will carry our curiosity into the galactic bulk. The next pillar of our stellar future is the mastery of propulsion. The impossible trajectories of Atlas have shown us that propellant-less drives and gravitational manipulation are not just science fiction. They are empirical realities. To explore the galaxy, we must learn to tap into the zero-point energy of the quantum vacuum, or create the localized warp bubbles that Kaku has theorized. This requires a unification of general relativity and quantum mechanics, the holy grail of physics. The presence of Atlas is proof that this unification has already been achieved by others. It is a call to our young physicists to solve the equations that will allow us to navigate the metric of space-time, rather than fighting against it. Furthermore, the architecture of curiosity requires a new approach to data and intelligence. 3I/Atlas, as a likely von Neumann probe, represents the peak of automated scout technology. As we expand into the solar system and beyond, our primary explorers will not be biological entities, but high-fidelity artificial intelligences housed in durable, radiation-hardened hardware. We must design a digital infrastructure that can operate independently for centuries, synthesizing data from distant star systems and reporting back through free space optical networks. The star cloud concept, moving our data centers into space, is the first step in this decentralization of human knowledge. We are building the crown of intelligence that will eventually allow us to monitor the entire galaxy as a single environment. But the most critical component of our future is not technological, it is philosophical. As Michio Kaku emphasizes, the arrival of an interstellar messenger is a reminder that curiosity drives progress. We must move beyond the naturalist bias that treats the universe as a collection of dead rocks. We must learn to see the patterns of intention in the dark. Designing our future means accepting that we are part of a larger galactic conversation. It means preparing for a world where the distinction between astronomy and contact is permanently erased. The silence of the void has been broken, and the story that follows will be written by our ability to ask the right questions. As 3I/Atlas fades back into the infrared darkness of the interstellar medium, it leaves us with a legacy of inspiration. It has shown us that the Great Silence was just a period of waiting. We are standing on the threshold of a new era, the era of the interstellar citizen. We are the children of a planet that has finally noticed its neighbors. By embracing the architecture of curiosity, we are ensuring that the next footprints in the cosmic dust will be our own. We are the architects of our own destiny, the designers of a future that is as infinite as our thirst for knowledge. The visitor has passed, but the question remains: are we ready to follow? The stars are calling, and for the first time in human history, we have the tools to answer. In the silence of the void, we find the roar of our own potential, and the journey has only just begun.